Hi, I'm Drew.
And I'm Zaina. Welcome back to the third episode of this virtual field lab series where we're searching for hope in our rapidly warming world.
The first two episodes really provided a lot of hope for the future. In both episodes, we saw evidence that we can make a positive impact on big global atmospheric problems that we cause.
The positive changes were made by collectively committing to bipartisan legislative solutions that change the human systems at the root of each problem.
In the first episode, we saw how people caused the problem of acid rain by burning too much coal with very little pollution control. But then we changed the system. In 1970, the US passed the Clean Air Act that mandated scrubbers be installed on coal-fired power plants. After just a couple of decades, sulfate and acid rain pollution, measured in ice samples from Greenland, dropped to close to pre-industrial levels. In the second episode, we saw how people caused the problem of excessive nitrogen oxides in the atmosphere by burning too much gasoline in cars that had little pollution control. And then we changed the system in 1975 by amending the Clean Air Act to mandate catalytic converters on cars. That one legislative change now has nitrogen oxide pollution dropping back towards pre-industrial levels.
In this episode, we're going to look for hope in phytoplankton that are the foundation of the food chain in the North Atlantic Ocean. We also want to take an in-depth look at how science is done.
A lot of people think science is just a big set of facts that you read about in school.
That couldn't be further from the truth.
We think science is so fun because it's constantly evolving and changing as we learn more and more about the world around us.
Science is something you do, not just something you learn.
Let's explore one example of doing science together. Our story starts with tiny phytoplankton living in the North Atlantic Ocean. Just like you and me, phytoplankton excrete different things as part of their daily life of consuming food and energy and growing, and all that requires excreting waste.
One waste product that phytoplankton release is a chemical called dimethyl sulfide, or DMS for short. In simple terms, you can think of DMS like phytoplankton farts.
Once DMS is released by phytoplankton into the atmosphere, it pretty quickly reacts with oxygen-containing compounds, like nitrogen oxides, to form methane sulfonic acid, or MSA for short.
MSA is a pretty stable chemical, and it stays in the atmosphere long enough to be transported and trapped in snow and ice on the Greenland ice sheet.
The level of MSA that we find in an ice core in Greenland can be used as an indicator or proxy for how big the phytoplankton population is in the North Atlantic. Higher MSA levels would be an indicator of a lot of phytoplankton farts and a healthy phytoplankton population. This is a good thing, since phytoplankton are the foundation for the food chain. Lower MSA levels in the Greenland ice sheet could indicate a decline in phytoplankton and some trouble for the whole North Atlantic food chain.
Back in 2023, a group of scientists made a ton of MSA measurements across the Greenlandic ice sheet. Here is a simplified data table with estimates of MSA levels at the start of each decade. This data will form the foundation for our investigation today, so let's pause the video to do a few things in your notebooks. First, transfer these data into your own notebook. Second, let's build a graph with the data so it's easier to look for trends. Third, do your best to draw a best fit trend line through the data that shows the story that you think the data are telling. When you're finished, hit play again, and Dr. Becky Alexander from the University of Washington will be back to compare graphs.
Welcome back to episode 3. I'm Becky Alexander, an atmospheric chemist at the University of Washington. This was really a difficult trend line to draw. I actually cheated a bit and made a graph of all the MSA data we have back to 1800. I see two things in this bigger perspective. First, there's quite a bit of scatter in the data, especially when we go back further in time. It appears to me that back in the 1800s, MSA levels fluctuated, but in general averaged at just above 2 ppb. With that knowledge, I think that these first 4 data points, up until around 1930, could be a continuation of the baseline pre-industrial MSA level. After 1930, though MSA values seem to start trending down, then comes these 2 data points in 2000 and 2010. Specifically in 2010, MSA levels seem to be going back up. Let's write this investigation question into your notebooks. What do MSA levels in the ice from Greenland suggest is happening to the food chain in the North Atlantic? I looked at this data and thought, is this uptick in 2010 the start of a new trend, or just some scatter in the data like we have seen in other parts of the MSA record? If you believe the 2010 data point is an outlier, then the trend in the MSA looks pretty dire. A study published in 2019 by a group of my colleagues suggested that the consistent downward trend in MSA data correlated with increased pollution from the Industrial Revolution. Based on the data they had available, their interpretation suggested that phytoplankton populations were in decline, and the entire food chain in the North Atlantic may be in trouble. This is the cool thing about how real science works. Scientists publish their results and interpretations in well-respected journals that are open for everyone to read and evaluate. This allows everyone else in the science community to evaluate their methods and interpretations of the data and join in their search for better understanding of whatever they're studying. When I saw this data, my first thought was, I wonder what has happened to MSA values since the last data available in their study from 2010. More recent data might tell us if 2010 was an outlier like they concluded, or actually is the beginning of a new trend. I started looking for more recent data, but finally realized that nobody had drilled in Greenland to collect MSA data since 2010. If I wanted the data, I was going to have to go and get it myself. Lucky for us, here in the United States, the National Science Foundation and the ice drilling program support this type of research. So in 2023, I left my family here in Seattle for 3 weeks and flew to the Greenland ice sheet with a team to drill ice cores that would contain MSA trapped in the ice between the years 1995 and 2022. This is actually easier said than done. Getting to Greenland involved flying on a C-130 military cargo plane to get to Summit Station. When you land at Summit Station, it's over 10,000 feet above sea level, and it takes a day or two to just acclimate before you can actually breathe and begin to work. Then there's the cold. We were there in May, and May is the springtime when daytime temperatures are often below -5 degrees below 0 Fahrenheit, even sometimes as low as -40 degrees. It was also very windy, which made it feel even colder. Finally, after a couple of days, the sun came out, and even though it was still cold and windy, we took the snowmobiles out and drove to the drill site. We had to drill our cores at least 5 miles away from Summit Station to make sure that no contamination from the station was in the ice. To get back to 1995, we used sidewinder drills that you hold in your hands. The cores were drilled down about 15 to 20 meters. At these shallow depths, the snow still has not had a chance to change completely to ice. What we brought up in our drill cores is actually a form of snow and ice called firn. Firn is more dense than snow, but not yet solid ice. We drilled 5 different cores so we could test multiple samples from the same years. The firn and ice from 1995 to 2010 will allow us to double-check our data with the older cores. The FERN and data from 2010 to 2022 will tell us if the 2010 data point was just scatter or the start of a new trend. It was fun being in Greenland, but it was great to get back home. The ice core samples we brought back were eventually shipped to South Dakota State University for MSA analysis. Let me turn things back over to Drew and Zaina, and they'll show you how the MSA data were dated and calculated. Hopefully, these new MSA data will tell us if the food chain is collapsing in the North Atlantic or if something else is happening that is causing a reverse in the downward MSA trend.
Thanks, Becky. Becky asked us if we could help with the MSA data. No problem.
Remember where we started. Phytoplankton in the North Atlantic release a chemical called DMS, basically phytoplankton farts. DMS reacts with oxygen in the atmosphere and forms MSA that gets deposited along with the snowfall in Greenland.
Becky sent the cores to the University of South Dakota for MSA analysis. They use an instrument called a Q-trap mass spectrometer for MSA analysis, instead of the ion chromatograph that we used for the first 2 episodes.
The technique they use is very similar to how we calculated nitrate levels in episode 2. They build a calibration curve using known concentrations of MSA. The equation of the line for the calibration curve allows them to determine the levels of MSA.
Here's a model of the fern core that Becky sent to South Dakota, along with different MSA values that they found at different depths in the fern. Now, we have MSA values at different depths of the core, but we have no idea how old the fern is at each depth. When we drill deep enough, there are often visible layers, almost like tree rings, that we can count to determine how old the ice is. If the snow and fern hasn't turned to ice yet, then it's hard to use visible layers. Lucky for us, there are other ways to estimate how old the fern is at different depths.
All sorts of chemicals from the atmosphere get trapped in the snow. One really useful ion found in the fern are sodium ions from sea salt. If you've ever tasted ocean water, it tastes really salty. It has a lot of sodium chloride dissolved in it. In the winter, the North Atlantic is known for having huge storms that produce huge waves. These big waves and strong wind put more sea salt and sodium into the air. When we analyze the fern, we see annual peaks of sodium ions every stormy winter. We can overlay an analysis of sea salt sodium concentrations on the fern core. The sea salt sodium peaks should allow you to estimate the year that correlates to each of the MSA values measured at South Dakota State.
Becky was in Greenland in the summer of 2023. This top layer of snow with lower sea salt levels would be from summer of 2023. The snow and fern get older the deeper you go. This first peak would be the winter of 2022 to 2023, so this next low area would be the summer of 2022. That means we can assign this MSA value to the year 2022. Let's add that to our data table. There's no MSA value in this next part, which would be 2021, but we do have MSA values in this core model at the next point, which would be 2020. Let's add the second data pair to our table.
We are going to let you determine the age of the remaining MSA values. Pause the video while you estimate the age of each MSA value using the sea salt peaks. When you're finished dating all the MSA values, hit play again, and we'll meet you back here to compare estimates. Welcome back. Sometimes it was hard to tell if there was more than one peak in one area. Here are the estimates for the dates of each MSA value that we came up with.
Now, we should have the data that we need in order to see if the 2010 uptick in MSA was just noise or the start of a trend.
Pause the video again and transfer all your new MSA data to your MSA graph.
After you plot the new data, see if you can modify or extend the trend line you drew so that it incorporates all of our new MSA data.
When you're finished, let's think about the investigation question that we wrote down at the beginning of this episode.
Becky asked, what do MSA levels in the ice from Greenland suggest is happening to the food chain in the North Atlantic?
Now, we have a lot more data to evaluate when thinking about that question. While you have the video paused, do a little analysis and write down 2 things that you notice and 1 thing that you wonder.
When you're finished with all that, hit play again, and Becky will come back to share with us what story she sees in this data.
Thanks, Drew and Zaina. Remember, we started this video by saying we were looking for hope for the future in phytoplankton populations in the North Atlantic. We also went looking for more data from recent snow and ice on Greenland to help us better evaluate the trends that suggested the base of the food chain in the North Atlantic may be collapsing. This is really a great example of doing science. Data is collected and analyzed, papers are published based on the best analysis we can do with the data available. Then all of our peers get to evaluate our work and collect more data themselves if they believe there is more to the story. I notice that now with more data, we have a very different picture of the trends in MSA levels in the Greenland ice. We have data that suggests that MSA levels in the ice correlate well with phytoplankton populations. But I started wondering if it was possible that something else in the atmosphere over the last 120 years was changing that relationship. Then I started to think about the nitrate data we analyzed in episode 2. If we look at the level of nitrates in the atmosphere between 1900 and 2000, the trend is almost a mirror image of the MSA values found in the ice in Greenland. I'm an atmospheric chemistry scientist, not a biologist, so I started to think that maybe the rising nitrate levels from transportation and electricity had a role in decreasing MSA values. It turns out there could be a connection. The chemistry is pretty complex. But when nitrate levels in the atmosphere spike, a chemical reaction can take place that converts the DMS being released from the phytoplankton to sulfate instead of MSA. The Clean Air Act of 1970 provides more evidence that nitrate levels were involved in the missing MSA. The small tail in MSA data visible in 2010 wasn't just some scatter and a downward trend, but was actually the inflection point showing MSA values rebounding to pre-nitrate pollution levels as a result of the Clean Air Act of 1970. If this new hypothesis is correct, that is great news for phytoplankton and the North Atlantic food chain. If possible, it's always good to check your work with other data. Let's take a quick look at MSA data from ice from Mount Denali, Alaska. If you look at the global wind patterns again, you can see that snow in Alaska is mainly impacted by pollution coming from China, not the United States. Nitrate from China is a pollutant that stays in the atmosphere long enough to make it to Alaska, but is removed from the atmosphere by rain and chemical reactions before impacting the snowfall on Greenland. China was expanding coal, oil, and gas use throughout the entire 1900s without pollution control like our Clean Air Act. You can see that the overall MSA concentration in snowfall in Alaska is decreasing. This type of evidence further supports our hypothesis that increasing levels of nitrogen oxides in the atmosphere from China are still reacting in the atmosphere with the DMS, released from the Pacific Ocean phytoplankton. The net result is this overall downward MSA trend that we still see in the snow samples from Alaska. So can we find hope for the future in the phytoplankton populations of the North Atlantic? The fact that the new MSA data now suggests that so far bioproductivity in the North Atlantic is not collapsing is definitely a good, hopeful thing. With that said, there are still a lot of human-caused pressures on the entire ocean ecosystem. Data suggests that increased runoff from Greenland and warming waters are slowing the Gulf Stream and the circulation of the entire Atlantic Ocean. Increased carbon dioxide and methane levels in the atmosphere are trapping more energy, causing ocean temperatures to rise. Increased carbon dioxide levels from burning fossil fuels are causing pH levels in the ocean to drop as ocean acidification increases. These are just some of the problems that we as a global population need to address. But as we have seen in the first two episodes, we are responsible for the changes that we are witnessing and measuring. But we have shown that we also have the ability to positively impact the planet by changing the systems that are at the root of each problem. Big bipartisan environmental laws like the Clean Air Act have produced measurable positive impacts for our generation. And I believe and have hope that a new generation can make a historic move to clean energy systems across the planet. My hope is that beginning that transition now will have a positive impact that your generation will be able to measure in the future. Thanks for joining us on this three-part series where we've looked for hope on our warming planet. I'm filled with hope that you will all be a part of implementing solutions that will take the whole planet toward a sustainable future.